it is.
Okay, for the analysis and visualization, we carried out analysis on the data to find outliers and understand patterns of incidents. So from what we found in the analysis, we observed from the data set about the incidents, we saw that major cause of incidents were from stationary vehicle. And this stationary vehicle could be as a result of maybe a car is parking where it's not supposed to be, or maybe a car is broken down, or one other reasons. Now, it was very surprising that most incidents were less of accidents and congestion came in more. We also saw weather condition on the low, and we also saw publicity on the low. I'll talk more on the weather condition and more views on the next slide. Now, from the analysis also, we also saw some erratic and very strange trends in the data. We observed that in 2016, it seemed there was a particular month data was not recorded, and that was in Q3. So we also saw that in August 2018, we had less record of data, and this is it here. This is 107 in August. So we assumed that, oh, maybe during that period, the government or the organization couldn't record more data, or they had issues with their recording system or database, because the mean value of incidents that happened per month where we saw was within 900 and 1,000. Then you having only 100 incidents in a month looks strange and unbelievable. So next, about our preprocessing model, what do we do about the preprocessing? We tried cleaning and handling missing data, but fortunately enough, we had some issues with some data changes. So a particular data was missing and another data was input in that type of data. So we had to look for nuances in data. We tried engineering more features. So for special related features about the road segment, we had to get the center of the road segment, the latitude and the longitude of the center of the road segment as a feature for our model. So we also had to get the suburban and the town of a particular road segment. Now we're not given that data in the main data set. So how did we get the suburban and the town? So what we did was we used a library called JoPy. What JoPy did for us was this: we presented the latitude and the longitude of the center of the segment to JoPy, and JoPy was able to reverse geocode the latitude and longitude and give us the location of where that latitude and longitude was. So from JoPy we were able to get we didn't need the country, but we were able to get the suburban and the town, and we were also able to get which road was closer to where the suburban is. Now we also got from the special data we had.
Could you speak up a bit?
Can you hear me now?
Yeah, it's okay.
Am I audible?
Yeah, it's okay now. You are audible.
Okay, also we got the road type from the geospatial data given by Zindi. So the road type, which type of road is it? Is it a major road? Is it a two-way lane? Is it a one-way lane? Then we also got the road length. Because now we were told that the length of each road segment contained about, at least it was not certain it was meant to be 500, but it was about 500 meters. So we were able to get the road length from data we were also given. We also found a way to get more time series related feature. So we can see, okay, behavior in time of incidents, in hour of incidents. Is it that more incidents happen during the weekend? Is it that more incidents happen during a particular period, during the working hours or during rush hours in the morning or in the evening? So we got time related features like hour, we got time related features like weekend, month, holiday. So this is a little snippet of the time related features we got. We use in getting our time hours weekend and other else. So this snippet, it's more, I got it from fast.ai library. I think since I saw this type of fast.ai library, it's really been helpful. Then also the weather feature. We also giving weather feature, but we didn't use weather feature for our final model. Why didn't we use weather feature our final model? Remember in the previous slide, we saw that the cause of incidence, weather, had very least cause of incident. So it wouldn't really have had more effect on our model, and we proved it. And when we trained with, when we added weather feature, our model didn't increase. Our model instead, it didn't improve the accuracy. So we were like, oh, weather feature is irrelevant. We took it off. Then we added lagging features, so these lagging features we did a combination of time series and geospatial data. These lagging features I added, they didn't really have any effect or much, didn't improve our accuracy, so we took it out. So initially we tried to create as much feature as possible we can think of. At the end of the day, we ended up creating about 70 features in total, but we ended up using only 14 features for our final model. Then the second pre-processing was converting our data set from the main data set to a particular data set that is fit for training our model. Remember, we were given only traffic incidents only traffic incidents data during a range of periods. So for each particular day, or not for each particular occurrence of traffic incidents, we are only given that the data ranging from 2016 to 2018. Now we had to look for a way to convert our data in such a way that we can train our model. Remember, for you to be able to train a model, you need your X value. Your X value is your predictor, and your Y value should be your predicted. So we needed to create the X value and the Y. Now the Y value consists of, since we are doing is a classification problem, it consists of two discrete value. Yes, if traffic incidents happen, and no, if traffic incident didn't happen. So we try to create, okay, can we get from the range of 2016 to 2018, for each hour, for each road segment, can we check if traffic incident happened based on this main data we had? So I think this preprocessing problem was, this preprocessing wasn't really of a big issue, because in Zinde's main site, where the data set, someone had already given a starter code that could help convert this data set to this. So during the conversion of this data, remember this data set has about 53,000 rows for only traffic incidents, and it contained about 5 megabytes of data. Now, on converting this data to this format, it gave us about 13 million rows of data sets. And now our Y value, that's the target value we are going to use for training, now contains about 0.9617% of non-traffic incidents, and the traffic incidents contain about 0.038%, and that was very highly imbalanced data. How do we solve imbalanceness of data? That was one problem our team was, okay, what should we do? Then moving forward, then how do we solve issues of memory issue? Now remember, I said that we had, our data was previously was about 53,000, and it became 13 million rows, 50 million rows. Now from 5 MB, it came to 2 gigabytes. The 13 million rows of data resulted to about 2 gigabytes. So now, how do we use 2 gigabytes when we have limitations in our local machine? How do we train a 2 gigabyte of data in our local machine? So we initially we resorted to using Google Colab in training the whole data set, but at a point in time, Google Colab was crashing because of memory issues. So we were like, okay, so what other alternative do we have? We came up with a snippet, or let's say an optimization function that could convert our data sets from the 2 gigabyte to 603 gigabyte. how did we do that? What we did is this. Now, pandas initially converts all columns under it, all the data type of each columns to int 64 bits if the data type is numeric. So what we did was this: we had to find the minimum data of each column and the maximum data of each column. Now, based on the minimum data of each column, minimum data of each column, if it fits a particular data set, data type, we use it as our data type. So what it means is this. Now, for example, a particular column contains of 0 and 1. Initially, pandas takes that particular column as int64, and int64 consumes a lot of memory in computer. So what we did is this. Now we check for, okay, what's the minimum value of that value is 0, what's the minimum value of that value is 1. Now, what's the mean of the value? The value is ranging between 0 and 1. Automatically, that value is a Boolean value. So a Boolean value doesn't really consume much memory space as int value. So we converted the value to Boolean. We did for other data type, check, oh, is this int 8, or is it int 16? Is it int 32? Is it int 8, int 16, or int 32? So that help us in optimizing, reducing the memory usage of that particular data type. So also, for us to solve another issue of memory usage, also we had to resolve using Google Cloud Platform, that was GCP. So one of our colleagues, he had a GCP Google Cloud Platform account, so he was able to create about 30 gig of RAM for us to use with Google GCP. So with Google GCP, we were able to train our model on the cloud on Google GCP. So this 32 gig is an estimate. I can't remember, but I think we used more than 32 gig of RAM. So then moving on to our validation strategy, we've solved our memory issue now. How finding a way, okay, our model is ready for training. How do we evaluate our performance based on our model on our local PC? Now remember, Zindi allows only 10 submissions per day. And with only 10 submissions per day, you can't really do many experimentation as possible, because machine learning, I think, is more about experimentation, about finding things, about trying what works and what doesn't work. So what did we do? So we had to split our data using a time series split from sklearn. Before we used our data with sklearn, we had to resolve, okay, since we have this whole huge of data, should we use all our data set in training or not? So initially, we tried using all the data sets in training initially, and we tested the accuracy on the leaderboard. And we saw that our accuracy was really, 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 really bad. We were like, what should be the problem? That's when we went to our analysis, and we saw this erratic version of data in August 2016. There was no input data within this month in 2016. And also, we also saw this erratic data in August 2018. From the previous slide I showed, we had about only 100 cases there. So how do we solve this problem? It's resolved to removing the month of this missing year, and also removing August completely from our train set. Even doing that, our accuracy wasn't still increasing. So we also resolved to, okay, can we use, one of my colleagues, we read an article, so he said, okay, can we use only 2018 data set? Because imperatively, when you're solving a time series problem, it's more advisable to use a year closer to your prediction. So it's not ideal for you to using 1990 data set and trying to predict the future of 2018. It doesn't look ideal. So we use that intuition and say, okay, let's imagine that 2016, 2017, the setup of database for traffic collection wasn't really that stable. We assume that, okay, now from 2018, the setup was more stable. And you can also see the trend data took from 2018. From 2018, it looks that the data set the incidents were already increasing. Don't be deceived by December having a high value. Because if you go back to this data set where we have December 2017, the value is also low here. And December 2016, the value is kind of large. So we resolve that, oh, we will have many issues using these 2 years, just 2016 and 2017. Let's use 2018 only. So that's how we resolved it, only using only 2018 for our train model. Then from this train model we had, how did we split it to create a validation set? So we use the library called time series split. Is a function from sklearn library. So what this library does is this. For it splits your data depending on the number of splits you defined for it. So the number of splits we defined was 8. So what it does is this. As with that 8 split, it takes the first set of fold, it trains on the first set and tests on the next set of fold. It takes the first 2 sets of fold, it trains on the first 2 and tests on the next. It takes the first 3, it trains on the first 3 and tests on the next. It does that till it's been able to exhaust the whole 8 fold it had been. So using this time series split, we had a very similar F1 score in what we had on our leaderboard. So we were like, oh, our validation strategy is okay. Let's try different experimentation on our work. So then moving on. Now, we've trained our model finished, we're like, okay, what else? What should be the problem? Remember, our data set is highly imbalanced. We had about 0.038% of incidents, and F1 score really penalizes imbalanced data. So what we did was this: we had to find a way. Okay, is there a way we can optimize this F1 score based on the threshold? So we resolved to optimize our F1 score, finding the appropriate threshold for the F1 score. Imagine the default default threshold for F1 score is always 0.5. But now we're saying, oh, is there a way we can reduce the threshold so at least our data can see a little bit of traffic incidents? Because when we resolved in using 0.5 as our threshold, all our data sets were predicting just 0.0000000. So we result to shifting the threshold a little bit further. So this is the code snippet we use in optimizing our threshold. So what this code snippet really did is that within a range of value from 0.11 with difference of 0.01 to 0.5, we had to find, okay, which optimal threshold would give us a very high F1 score. And also we used this F1 score, we did this optimization based on our local validation we had from the previous slide. Then the modeling, how did we go about the modeling? So we started with LightGBM. LightGBM, our data set is a forecasting problem, it's a classification problem. And there was an article I read on Kaggle, not on Kaggle, it was an article someone wrote. It's a paper, a paper on Kaggle. So the person tried to look at the trends in time series problem solving in Kaggle from the year Kaggle started till present, and he observed that mostly for forecasting problem, or time series problem forecasting, that mostly gradient boosting models are the ones winning, or are the ones solving time series problem with a higher accuracy. So we said, okay, what are the gradient boosting model we can use? Extreme gradient boost, LightGBM, CAD boost. So we resolved to using LightGBM because LightGBM is faster than extreme gradient boost. So, and we wanted something that would would allow us to do faster iteration or faster experimentation with different models and different ideas. So we resolved, okay, LightGBM should be our bet. So we use also this LightGBM for feature selections, also using the feature importance of LightGBM in selecting our best parameter. Then for hyperparameter optimization of the LightGBM, we didn't use any complex algorithm in hyperparameter tuning. So hyperparameter tuning was based on the feedback we had from our local validation, or that is from our our cross-validation score we had. So this hyperparameter optimization, the only hyperparameter we really tuned was the maximum depth, and we tuned the maximum that we tuned the subsample. So we tried, because light GBN doesn't really overfit that much. So we tried a maximum depth between range of 10 to 15 to see how well it performs. So the more it overfits, we try to reduce the maximum depth. Then for the then when we were done with light GBN, we were satisfied with that, with our model with CAD GBN. We were like, okay, can we add more variety to our model? Let's use CAD Boost with the features Light GBN was able to give us. So what we did was this: we trained our final models as our final parameter with CAD Boost, and we also trained our final parameter also with Light GBN. Then for the final submissions, we averaged the output of the probability of CAD Boost and the average of the probability of CAD Boost and probability of Light GBN, and we used a threshold of 0.06, the threshold we got from our from the optimization of our F1 score. With this average, we were able to finish. We were able to have this score on the leaderboard. That was 0.2. We were able to finish the fourth. We finished fourth on the leaderboard. That's at the end of the competition. But I think fortunately, will I say fortunately for us and unfortunately for those in the first three, one of them we had issues with submission file or reproducing his score. Then we jumped up to the first position. Then so conclusion. Now, we observed from what we did, it was a very, 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 very interesting and very, very educative competition, because we learned a lot about geospatial data. We learned a lot about solving a machine learning problem. So we also observed that analysis and good data is better than a complex model, because I think we didn't really do anything supernatural in our data. I think what really gave us a very good head in our data was how we could see the trend in our data, and we were able to find out what should be the best data or what should be the best data to use for our final model. That's what really gave us the edge. And also memory, we also had upper hand from memory issues, because we were able to carry out many iterations because of the high number of memory we had from Google GCP. So we were able to try different things. I can remember when one of my colleagues, he tried training 2016, actually only 2017, 2018. He tried different combination of the data to see which of them would give us a better model, a better accuracy. And also, utilization of features is as important as possible. Now, if you look at the leaderboard, you see the difference between the first and the second. Let's say the difference between the first and the second, the third, and the fourth. The second, the third, and the fourth, they are almost on the same range. But the first, the gap was really, really wide. And from reading the blog on the first position, we saw that the first position optimized was able to use SAMRA data this SAMRA data that I talked about, that captures the number of moving vehicles by a particular camera per hour. So it's from the blog itself, on the winning solution itself, it said it was able to optimize, it was able to use that data. That was one of the, I think that was the area we didn't really optimize, or that's the area we didn't really look into. Maybe if we had looked into that, we would have also had a very, very high IQ. So very good data. It's very, very useful that you try as much features you have as possible when solving machine learning problem. You try what works, try what doesn't work. It's all about experimentation. How fast can you think? And also experience also comes into play. Then also, as I always say, better machine enhances the faster experimentation. If you have a very good machine that can enables you to train a particular model within few seconds, so you can try different another idea. It also gives you an upper hand. Then also versioning of code and work is very, very important. I still remember in the competition when we were asked to submit our best score. I remember we were not able to produce our best score. We had having issues in producing our best score before we were able to see a particular notebook or a particular hyperparameter that could give us the best score. But it was really it was really time taking and it was really frustrating. So that was one of the lessons I really learned in this competition. Versioning of your code is very, very important as a data scientist. For each code you write, for each changes you make, for each summations you make, it's very important you version your code. So if you want to version your code, you can try GitHub, GitLab, any versioning tools you can think of. So it's very, very, very important. Then I think also trying different machine learning models is very important in solving machine learning problem. A particular model might be good for a particular problem, another model might not be good for another problem. So it's very good to become versatile with both model. I'm going to talk about the modeling part because of the card boost we used here. On our public leaderboard, our light GBN was the best score on our public leader because we submitted light GBN, we submitted card boost. Our light GBN was the best score on our public leaderboard. And when we took the average of the output of card boost and light GBN, single of light GBN was still the best score. So what I'm talking about the multi machine learning model is this. Now different models are able to see different patterns or different aspects of your data. So if it's very good, you would know how to utilize different models, and also it's very good you know what type of model work in what type of problem. So if we had not averaged, or if we had believed on our light GBN score on the leaderboard and said, okay, light GBN is the best, we are good with it, and we didn't average the output of card boost and light GBN, we wouldn't have even beaten the first five. Maybe we would have finished around 6 or we would have finished around 7. So when you're doing competitive machine learning, ensembling at the final end of your experimentation is very, very, very important. So data cleaning rates, and you're very confident about your single model. It's very, very important to ensemble your model so you can have the confidence that, oh, in case a particular model is not overfitting to a particular set of features, a particular set of problem. Yes, that's it's all for now. So I would like to thank John for the opportunity to speak on this. I also like to thank Zindi for the opportunity to speak on this work of ours. Thank you. So if you're having any question, you can ask. I'll be ready to answer your question. Then
Okay.
also, yeah, okay.
Yeah, thank you very much, Wari, for your presentation. That was really insightful. So we have like 10 minutes left, so we can take some few questions. Maybe let me get started. First of all, looking at the imbalanced nature of your data, how did you handle that one? I think I missed a bit of
okay, the imbalance nature of our data. We tried downsampling. We tried different methods. We tried downsampling. We tried upsampling. We saw that downsampling of our data, that's reducing the numbers of zeros that data set, wasn't really helping. It was still giving up. So how did we solve the imbalanced nature? This was the way we solved the imbalanced nature of our data. We solved it using the matrix optimization. So the F1 score optimization or threshold optimization. So we had to reduce the threshold to go towards the range of the imbalance. Now remember, our data set the traffic incidents had only 0.038 value. So if you are using a threshold of 0.5 for you to get an F1 score, your value of all your data set will predict only non-traffic data. That's just 0. So for us to solve that problem, we had to reduce our threshold to between 0.5 and 0.06. That was using this threshold optimization script we had. So, but we finally resolved using 0.06 threshold for our final threshold.
Okay, so that's upsampling, right?
That's
So
yes, like that's kind of sampling, but not with the data sets.
okay. So if any of you has a question, you can unmute yourself and ask Wari. Okay. I think there aren't so many questions. So could you just elaborate when you talk of versioning? Just break it down.
Okay, versioning. Okay, when I
Yeah,
talk
how did
about
you guys do it?
okay, I
Practically.
practically on versioning. Okay, during the competition, we didn't do versioning of our code. So that's one of the issue we had in reproducibility of our code. So practically for versioning, what I advise is for when you are solving a problem in data science or maybe any machine learning competition, you should create a GitHub account when you're solving a problem. And for each changes on your code in that problem, you should commit your code to that GitHub account. Now, what versioning helps you in doing is this. So for each changes, you make a comment on the changes you make, then you commit. That you push the code to the cloud. You make when you make another changes, you write a when you make another changes, you write a comment, you push the code. So for vector, if you want to reproduce a particular aspect of your code, remember, oh, I versioned my code, maybe I made a comment somewhere, you go back and say, okay, at what version of my code was I able to make that comment? You go back to your GitHub account, and automatically, once you go to your GitHub account, automatically through that code, you'll be able to, through that that comment, you'll be able to see the particular code that you're looking for. So versioning is a particular, will I say, is beyond this paper. So it's a different topic, a different field on its own.
Yeah, of course. So by the way, is there anyone with a question? All right. So Wari, you mentioned that you created about 90 features. I mean, you had about 90 features in general, and
Yeah,
then you used 14 for your final
yeah.
model. Could you highlight those features you used finally? Could you just highlight them?
Okay, the features we use finally. I
Yes.
I didn't bring them on my slide, but I can
Yeah, I mean,
I
you
can
could just
share a snippet of. Okay, this is the final features we used for our model. So the features we used for our model finally was the road segment that as we had should be about 30 to 40 road segment. So we used the road segment as a categorical feature. We used hour, whereas the hour of when the incidents occur. We used the day of the week it occur. We used is it a weekend? We used is it on holiday? We also had a one of my colleagues, our sign our call. So why did this? Normally our is almost is circular. So what he created a a he created additional feature based on the circular nature of our sign and our course. We use the latitude and the longitude of the road segment. That's the center of the road segment. That's the longitude. Then we also use accident happen. So for each road segment, we try to find, okay, what's the number of incidents in each row segment. So we use them. We also use the sub one. This one we got from Joe, reverse Joe coding from Joe Pi. We used the road length, we used the road number and soft type. Yeah, this one we got the soft type from the geospatial data from the, so this these the features we use. Then, okay, so
yeah.
Then for the, okay, let me see if I can show. Then for the memory reduction function, that's the memory optimization. That's where we reviewed our data set from int 64 to different data type that fits the type of data column. So this is the snipe. This is type very good. Now we got this snippet from Cargo. There was one of Cargo's competition that people were complaining about memory issue, and one of the there was someone released this snippet on one of the discussion forum. So this is the snippet. So this snippet helped me convert our data set, if you see, from about 2 giga about 2000 MB, that's approximately 2 gig, to about 600 MB. So the reduction was in about 70% reduction. So that's I think when you handling big data, this snippet, it's a very good good for you to use.
Yeah,
Okay.
that's very nice, and for sharing with us.
Yeah.
Thanks very much. I don't know if anyone has a question else. I think our time is almost up, so we could call it a day. Thank you very much, Wari, and thank you everyone for joining. Thank you for Zindi for hosting and giving us your willingness to talk to us. I am John Bagiliko, the team lead of AI Ghana, and yeah, we are happy to be bringing you every Saturday the webinar. Someone will come to talk to us about how they solve their problem, especially the Zindi winners. So thank you once again, and hopefully we'll see you next weekend. And if you are interested in presenting something, especially if you've competed in a Zindi competition and you would like to share your solution, get in touch with us, and then we can make the necessary arrangements. Thank you very much, and have a nice weekend. Bye.